Welcome. My presentation is on the biomechanics of head and brain injury. This subject was the major focus of my research for the majority of my career, in which I served as a senior researcher in biomechanics for the U.S. Department of Veterans Affairs for about 20 years. And I'm also a courtesy assistant professor in biomedical engineering at the University of South Florida. Though I don't know if it's a true conflict, in the interest of full disclosure, I serve as a forensic consultant in personal injury cases that involve traumatic head and brain injury, such as helmets, motor vehicle crashes, and motorcycle accidents. So let me throw this out there. It takes about 1,000 pounds of force to the head to kill an adult human. Let's break that down and figure out what it means. We know, based on Newton's second law, that force is the product of mass times acceleration. It's not the speed that kills you, it's how quickly you come to a stop, as depicted on the t-shirt. So, the references are presented in the footer on each slide. Effective mass for a head impact is the sum of the mass of the head plus 1/2 the mass of the neck. With reference to the textbook by Chaffin and Anderson, the head weighs about 6.2% of total body weight, and the neck weighs about 2.2% of total body weight. So head plus 1/2 neck is about 7.3% of total body weight. Now, the mean weight for a U.S. adult male is about 198 pounds. Therefore, the effective weight of the head and 1/2 of the neck is 14.4 pounds, or effective mass 6.5 kilograms. And the average weight of a U.S. adult female is about 170.5 pounds. Therefore, the effective weight is about 12.4 pounds and effective mass about 5.6 kilograms. So, if we take the average of those two, we could substitute it into the equation as a generic constant for mass, or for effective mass of 6.1 kilograms. So we can say force equals 6.1 kilograms multiplied by acceleration. Therefore, force is a function of the acceleration or deceleration, where acceleration is the rate of change of velocity with respect to time. Now, velocity, when it comes to a fall-related impact, can be calculated as a function of the fall from height, where velocity equals the square root of the product of 2 times the acceleration due to gravity times the height of the fall, where g is the rate of acceleration due to gravity, 32.2 feet per second squared, or 9.8 meters per second squared. And the plot to the right shows impact velocity as a function of fall from height, and we can see that it is not a linear relation. In fact, a fall from only 1.2 inches will generate an impact velocity of 1.7 miles per hour, whereas a fall from 20 feet will produce an impact velocity of 24 miles per hour. We see, in fact, that much of the velocity is generated within the first 6 feet of the height of the fall, which equates to about 13 miles per hour, whereas if we more than treble that height to about 20, we're generating about 25 miles per hour, which is not 3 times the impact velocity. So if it's the rate of change of velocity with respect to time, now we see that impact duration has the greatest effect on force. I've done a lot of research in this area, looking at the hardness of different materials and how they affect impact duration. I've learned that An impact on steel is complete within about 2.2 milliseconds. For concrete, it's a little longer, 3.4 milliseconds, as shown by the left graph, whereas grass is in the order of 26 milliseconds, or more than 10 times that of a steel head impact, or head impact on steel. So as I said earlier, the threshold in terms of force to cause fatal injury to the human head is about 1,000 pounds. Or in SI units, that's 4,482 newtons. So mass times acceleration is 4,482 newtons. And we can substitute the generic constant for mass of 6.1 kilograms, rearranging for acceleration, which is force divided by mass. We calculate that it takes an acceleration of about 75 Gs to cause such a fatal head and brain injury. So, where acceleration is the rate of change of velocity with respect to time, let's use the impact duration of concrete of 3.4 milliseconds, and using that we determine that the impact velocity required to generate that amount of force is only 2.5 milliseconds, and again using the v equals square root of 2gh equation. Rearranging for h gives us v squared over 2g, which tells us that a fall from only 0.3 meters or 1 foot is enough to generate this 2.5 meters per second and result in a fatal head injury. Whereas if the fall were on grass, then we have a much longer impact duration of 26 milliseconds, and it takes a much greater impact velocity of 19.1 meters per second. Again, putting that into the equation, we get a height of 61 feet, or 61 times that required for head injury on concrete. So we've learned that impact duration is the critical factor, and that is determined by the compliance of the surface on which the head is impacted. Let's change gears for a moment and talk about mechanical properties of brain tissue. The brain is about 73% water, and like water in a syringe, it's highly incompressible. The brain is also highly deformable, like jello. So it's like jello in a bowl and has very low resistance to change in shape. Another property is that brain tissue is viscoelastic, which means it's both viscous and elastic. The tissue properties are time dependent. So again, remember that impact duration issue. Brain tissue is also heterogeneous, means that the properties are different in different parts of the brain, not only between the gray and white matter, but also within the white matter and within the gray matter. And lastly, brain tissue is anisotropic. There are different properties of the tissue in different directions, which explains why injuries differ between sagittal and coronal plane impacts, which we'll get to a little later on. All impacts produce both linear and angular kinematics, and the distribution of those linear and angular kinematics depend upon whether the impact vector is directed through the center of mass of the object or oblique to it. Let's think of this in terms of a home run versus a foul ball. If an impact is through the center of mass of a baseball, it produces the greatest translational force, which in turn is demonstrated by the greatest linear displacement, linear velocity, and linear acceleration. In other words, a home run. Whereas if the impact is more oblique, it produces a greater tangential force, which is evident in terms of its angular displacement, angular velocity, and angular acceleration, or foul ball. Similarly, impacts to the head, whether transmitted through or oblique to the center of mass, result in linear and rotational kinematics of the head and brain. So in the upper series of images, we see that the impact direction is through the center of mass of the brain, which results in a large linear kinematic response and a relatively small angular response. And the types of injuries associated with these linear forces are skull fracture, subgaleal hematomas, contusions, and epidural hematoma. Whereas, if the impact is more oblique to the head, it produces a much larger angular or rotational motion of the head and brain relative to a rather small linear component. And this results in brain injuries, diffuse brain injuries such as concussion, diffuse axonal injury, intracerebral hematoma, and subdural hemorrhage. So, as we showed, focal injuries are caused by the forces associated with linear acceleration, including skull fracture, subgaleal hematoma, contusions, and epidural hematoma. Whereas diffuse injuries are caused by forces associated with angular acceleration, such as concussion, diffuse axonal injury, intracerebral hematoma, and subdural hemorrhage. Let's talk now in terms of thresholds for head and brain injury. Skull fracture threshold is very different between adults and babies because of the mechanical properties of the skull in babies whose head can be easily deformed for the birthing process. So we'll focus on adult skull fracture thresholds. Ono conducted an extensive series of studies in which he impacted 25 gel-filled human skulls that were covered with the rubber skin of a crash test dummy, and determined that the skull fracture threshold in the frontal and occipital regions was about 250 Gs at 3 milliseconds, reducing to 140 Gs for impacts greater than 7 milliseconds. Whereas a lateral skull fracture threshold is 120 Gs at 3 milliseconds, reducing to 90 Gs for impacts greater than 7 milliseconds. So again, we need to pay close attention to the surface involved in the head injury to know which duration needs to be applied and therefore the threshold for injury. Brain injury can be broken down into 5 categories based on the abbreviated injury score, 1 through 5, starting with mild concussion, through 5, which is critical brain injury, such as acute subdural hematoma. Studies have shown that concussions and diffuse brain injuries do not occur in linear-only impacts. Rotational forces are indeed required. But it takes less force to tear a nerve axon than it does to tear a blood vessel. So if you have a hemorrhage, then there's good chance there's also axonal injury. Research has been conducted by Lowenheim and Depreter, 2 separate studies, where they defined the threshold for subdural hematoma as a function of peak angular acceleration of the head and impact duration. And we see for impacts on hard surfaces such as steel or concrete that are in the 2 to 3 millisecond range that would take a very large amount of peak angular acceleration to result in a acute subdural hematoma. But as the impact duration increases, particularly beyond 10 milliseconds, and that would be associated with the use of protective headgear or impacts onto more compliant surfaces such as grass. And so we're talking about sports such as equestrian sports or football. Then you see there's a much greater risk of acute subdural hematoma associated with these longer duration head impacts. So in summary, more likely to sustain a skull fracture with an unprotected head on a hard surface, whereas more likely to sustain a brain injury with a protected head or a head impact onto a more compliant surface. Leave you with this point: bounce is bad. If the head impacts a surface in which neither the skull nor surface is significantly deformed, then the skull will bounce back. The relative impact speed between the still forward moving brain and the backward moving skull is nearly twice that it would have been if the skull had simply stopped. So you see that the skull impacted the surface first, the brain is still moving forward, the skull then rebounds and the brain is again still moving forward, so you have that motion of the skull in the opposite direction of the brain, which doubles the total impact velocity. Finally, these are a couple of graphs of some of my ongoing research. The first is unhelmeted head impact onto concrete. And in the upper graph, you see it's got a very high peak linear acceleration. So significant risk of skull fracture along with a much shorter impact duration. So we have a lower risk of brain injury. In the bottom graph, you'll see that the rebound in terms of peak angular acceleration is particularly low. Whereas for a helmeted head impact onto grass, while you have in the top graph a much lower peak linear acceleration, therefore lower risk of head injury, the impact duration is almost 10 times that of the unhelmeted or unprotected condition, which results in a significantly higher risk of brain injury. And if we look at the bottom graph, the rebound effect, in fact, the peak angular acceleration at rebound is even greater than that, than it was in the initial impact. And with that, I will gladly take questions.